So in this question, we're looking down on a boat, and in this question, we're told that a fisherman comes along to help pull the boat. So we've got two fishermen. Each fisherman pulls with a force of 300 newtons. So these two vectors represent the two fishermen who are pulling on the boat in slightly different directions. We're told that diagram 2 is drawn to scale. So if you have a look, you will see that this vector arrow is 300 newtons, and if we measure it, you will see it's 3 centimetres long. The second arrow also represents a force of 300 newtons and is also 3 centimetres long. So you've got 1 centimetre per 100 newtons. We're asked to add to diagram 2 to show the single force that has the same effect as the two 300 newton forces. And we are to determine the value of this resultant force. In order to answer this question, we are going to use the parallelogram law for the addition of force vectors. So if we've got two force vectors acting on a body, that's these two forces here, and we want to replace the two vectors with a single vector that has the same effect on the body, we can use the parallelogram law for the addition of the two vectors. So the first thing we've got to do is accurately draw or accurately turn these two sides into a full parallelogram. And what we need to know is the angle, this angle here, between the two vectors. So we're going to use our protractor to measure that angle. And you can see that that comes out at 0, 10, 20, 30, 40 degrees. So what we're going to do then is use that 40 degree measurement to figure out where to draw the remaining two sides of the parallelogram so that they are parallel with the opposite side. So remember that angle is 40 degrees, so we're going to go around from here, 0, 10, 20, 30, 40. There. So we put our pencil on the point of the force vector, and we're going to draw our line in that direction towards the point that we made. So we now know that this line is parallel with this force vector here. We're going to repeat that process. So again, remembering that 40 degrees, there we go. So 0, 10, 20, 30, 40. So we put a little dash on the 40 degrees there. We're going to put our pencil onto the force vector, line it up with the 40 degree mark that we made. Draw along there. So we know that this line is parallel with this line here. So now we've got our completed parallelogram. In order to find out the resultant force, what we do is we draw in a line across the centre of the parallelogram. There we go. So this line represents the resultant force in the parallelogram law. And if we measure the length of that line, you see it comes out to 5.5 centimetres. Now, we'd already established that each centimetre represents 100 newtons. So if we have a line of 5.5 centimetres, then that tells us that the resultant force is 550 newtons. And they've given us the unit there. So here's another example of how you might use a scale-drawn vector diagram to figure out the magnitude of a force or forces. Let's read the question. Figure 14 shows a small aircraft being used to tow a glider. So here's our small aircraft. Here's a cable connecting it to a small glider. We're told the tension force in the cable can be resolved into a horizontal component and a vertical component. The tension in the cable is 2,000 newtons, so that's the force through that cable. The cable makes an angle of 20 degrees with the horizontal, so this angle here. We are asked to draw a vector diagram to determine the magnitude of the two components, that's the horizontal and the vertical components, of the tension force in the cable. So here is how I would draw that vector diagram. I would begin by drawing a horizontal line, or a line to represent the horizontal. At this stage, it doesn't matter how long that line is. You'll see why in a second. Here we go. I'm then going to use my protractor to draw, or to measure, an angle of 20 degrees, because we are told that the tension force is at an angle of 20 degrees to the horizontal. So I'm going to put a little line at 20 degrees, so that's 0, 10, 20 degrees, to help me draw in the tension force. Now this has to be a scale diagram. So the scale that I'm going to use is going to be 2 centimetres for every 1,000 newtons. Therefore, if the tension force is 2,000 newtons, then my line representing the tension force will need to be 4 centimetres. That's 2 centimetres per 1,000 newtons. It will need to be drawn from the end of the horizontal at an angle of 20 degrees. So I've got to line up my ruler with that 20 degree mark I made slightly earlier. And the line will need to be 4 centimetres long. We want to make that as accurate as we possibly can. There we go. Now, the vertical component is obviously going to be perpendicular with the horizontal component. So that means the angle between the vertical and the horizontal will be 90 degrees. This angle we already know is 20 degrees. So 90 plus 20 gives us 110. Angles in a triangle add up to 180 degrees. So we know that the angle between the tension force and the vertical must be 70 degrees. So we can use that to help us draw a really accurate vertical component. So we're going to line our protractor up with the tension force, and we're going to mark 10, 20, 30, 40, 50, 60, 70 degrees. So that's there. We're then going to draw in the vertical component of the force by lining up our ruler at the end of the tension force and the 70 degree mark that we've just made. There we go. And you can see that our 3 forces have made a right angled triangle. So I've got our tension force, the vertical component of the tension force, and the horizontal component of the tension force. We now need to measure the length of our 2 forces. So the horizontal component, ooh, that's tricky, look at that, comes out as, so there's 3.5678, look at that, it's halfway between 3.8 and 3.9. So we're going to say that is 3.85 centimetres. Our vertical force there is coming out as 1.4 centimetres. So you'll remember 2 centimetres was 1,000 newtons on my scale. So in order to figure out the 2 forces, I simply need to half 3.85 and multiply by 1,000, 1,925. And similarly, I will take my 1.4 centimetres, divide by 2, multiplied by 1,000, giving me 700 newtons. We're given the units there. So we have resolved the single tension force into a vertical and a horizontal component.